All right, welcome everyone. Today we are diving headfirst into a real statistical powerhouse, the t-test. Think of it as this amazing tool that researchers pull out when they need to test a theory. But, and this is the key part, they're missing a critical piece of information about the bigger picture they're studying.
So let's kick things off with a classic research puzzle. I mean, this is something that scientists and researchers run into all the time. Imagine you've got this great hypothesis. You've gone out and collected your data from a sample. But then you hit a wall. You realize a super important piece of info about the larger population you're studying is just gone. It's missing. So what do?
And trust me, this happens all the time. Let's say you want to know if a new teaching method actually improves test scores for a bunch of students. Okay, simple enough. You can totally compare their scores to the national average, right? But here's the snag. You're missing that critical clue about how spread out all those national scores really are.
And that right there, that's the heart of the problem. We might know the population's average score, you'll see it represented by the Greek letter mu, but its true standard deviation, or sigma, that's almost always a mystery. And just as a quick refresher, standard deviation is just a fancy way of saying how spread out the scores are. Without knowing that spread, we have no way to be sure if our sample is genuinely different or if it's just a random fluke.
Okay, so you might have heard of the z-test. And look, the z-test is great, it's fantastic. But it's a bit of a rigid tool. It requires you to know that population variability. It absolutely needs that missing clue. The t-test, on the other hand, well, that's our flexible smart tool. It's designed specifically for this exact situation, when you're working with, let's be honest, incomplete information, which is most of the time.
Okay, so how on earth does the t-test actually work? I mean, what's its secret? Its real power is in this really clever way it has of working around that missing puzzle piece. Instead of demanding to know the population's true variability, it just estimates it.
So here's the key thing to remember. A t-test is a formal hypothesis test that lets us compare our sample to a population even when we have no idea what the population's variance is. And the way it does this is pretty brilliant. It just uses the variance from our own sample data as a stand-in to create this special tailored comparison distribution.
All right, so educated guess sounds good, but how does it actually do it? I mean, the t-test doesn't just pull a number out of thin air. It uses a pretty sophisticated toolkit to make sure its estimate of that missing variability is as accurate as it possibly can be.
Okay, tool number one in the kit, the unbiased estimate of the population variance. Now, what it does is it uses a slight tweak in the formula. Instead of dividing by n, the number of people in our sample, it divides by n minus 1. And that little change does something amazing. It generates the most accurate possible guess for the population variance, all based on the data we actually have from our sample. It really is our best guess.
The second tool is degrees of freedom. I know, it sounds super complex, but the idea behind it is actually pretty simple. See, to calculate the variance, we first have to know the mean of our sample, right? Well, once that mean's locked in, only some of our scores are truly free to be any value they want. By subtracting 1 from our sample size, we're basically making a more conservative, more accurate estimate. And this is especially important when we're working with smaller samples.
All right, enough theory. Let's put these tools to work. Our first scenario is the one-sample t-test. This is the one you're going to use when you have a single group of people and you want to compare their average score to some known standard or population mean.
Check out this question. Did our mindfulness program significantly improve attention span compared to the national average of 15 minutes? This is a perfect question for a one-sample t-test. See, we've got one group, the program participants, we have their scores, and we have a known population average, 15 minutes, to compare them to. But what's missing? You guessed it. We almost certainly don't know the standard deviation of attention spans for the entire nation, and that is why we need the t-test.
So to get a solid answer to our question, we followed this really systematic 5-step procedure. First, you state your hypotheses, the null and the alternative. Then, you set your decision criteria, like what counts as a significant result. Step 3, you use your sample data to figure out the characteristics of the comparison distribution. Fourth, you collect your data and crunch the numbers to get your t-statistic. And finally, step 5, you make a decision based on that statistic. It's a clear, logical path that takes you right to an answer.
Okay, so that's great for one group. But what if your research question is all about change over time? What if you want to compare a group to itself, like in a classic before and after study? For that, we need a different flavor of the t-test.
It's called the dependent samples t-test, or you might hear it called a paired samples t-test. It's perfectly designed for these repeated measured situations, where you're tracking changes within the very same people over time.
Now the key insight here, the real aha moment, is the shift in focus. Forget about the raw scores for a minute. The entire logic of this test now centers on that final column you see there, the difference scores. We're not comparing our group to some population anymore. No, we're analyzing the change that happened within each and every individual.
So our research question completely transforms. Now we're asking, is the average change significantly different from zero? It's pretty clever, right? By focusing on these different scores, we've turned what looks like a two-condition problem into a much simpler one-sample problem. We're just asking, on average, did our intervention cause a real measurable change? Was there an effect or not?
All right, so we've just walked through two incredibly useful versions of this test. We've seen how they work around that missing information to find answers, so what's the bottom line here? What's the big takeaway you really need to remember?
Okay, here it is in a nutshell. The t-test is your absolute go-to statistical tool whenever that population variance is a mystery. If you're comparing one group to a known standard, you're going to use the one-sample t-test. If you're looking at before and after scores for the same group of people, you'll want the dependent samples t-test. And just remember, these tests are powerful, but they work best when their assumptions, like the data being roughly normal, are met.
But what happens if your data isn't perfectly normal? Should you just panic? Absolutely not. One of the great things about statistics is there's usually a plan B. If the assumptions for the t-test are seriously violated, you can pivot to a really robust alternative, like the Wilcoxon signed rank test. It doesn't rely on those same assumptions.
You know, at the end of the day, the t-test isn't just some dry formula in a textbook. It's a whole framework for asking better questions, especially when you don't have all the answers. It's a flexible, powerful tool for finding the real signals hidden in all the noise. So, I guess the final question to leave you with is, what real-world puzzles could you now investigate with this tool? What answers are out there just waiting for you to find them?